Hello, I'm Selma. My team and I will talk about our project Kuwave.
Outline, Introduction, Alternative Solution, Concept Selection, Initial Design, Design Shortcomings, Design Improvement and Description, Detailed Design, Manufacturing, Full Assembly and Budget, Future Work, Conclusion. Introduction. Energy is the main resource driving the economy of all countries in the globe. The world population is increased and expected to reach 9 billion by 2050. With increased population, the energy consumption is also expected to increase, increasing greenhouse gases emission from coal and hydrocarbon-based power plants. So, it is protected that renewable energy source will be used in the future to meet the energy demand. Renewable energy is energy that is collected from renewable resources. It is eco-friendly and emits little to no greenhouse gases into the air. In the last decade, renewable energy has gained a foothold in many countries. However, in Kuwait, electricity generation still relies almost exclusively on fossil fuels. Renewable energy comes in different forms, such solar and wind, which are actually being developed in Kuwait. Another form of renewable energy is wave energy. Wave power is the transport of energy by ocean surface waves. Wave energy extraction was never really considered in Kuwait. Through our research, we found out that there actually is location where the wave characteristics seem to be very promising for power generation, which is Maradim and Garo Islands. The wave height in this area goes up to 2.5 meter, which is a good sign since 1 meter high waves are preferable for electricity generation. The wave period varies from 2 to 6 seconds. The water depth is between 19 to 30 meters, measured about 1000 meters away from the island, where the device will be placed offshore. The wave power potential varies from 0 to 16 kilowatt per meter. With an average of 2 kilowatt per meter per wave crossing, this amount of power is expected to be sufficient for the utility service in the island. Facility in Maradim include a security point and a port warship stop. A one big environment crime is being committed in this island. Gas generators are being used here to power the area, which cause massive noise, leakage that pollute and is extremely dangerous on marine life. It should be noted that Garo Island suffer from major erosion problems. Based on the information discussed, there are some standards that we intend to meet. A mechanical efficiency greater than 50%, electricity efficiency of 90%, a power output greater than 0.75% kilowatt per meter per wave crossing. The expected life in service of the device is around 20 to 25 years, operating around the clock. Alternative solution. After studying the different types of category which are wave-activated bodies, overtubing terminator devices, and oscillating water column devices, it was found that wave-activated bodies would be best suitable. To convert wave energy into electric energy, the device must go through three stages to complete the process, which are front-end energy, BTO system, and electric generator. There are many different types of each stage, so we made combination of this to generate the design concepts. Here are the 9 generated concepts. Concept selection. After generating the concepts, it was time to evaluate them, taking into consideration the BDS. A Bow chart was used to compare them to an existing design, which in our case is developments. From the chart and some further research, Concept 5 was found to be the best due to use simplicity and case of implementation. Initial design. We have a non-floating cylinder connect to an arm and a countermass on either side. As the wave rise and fall, the cylinder will go up and down, causing the arm to rotate. This rotary motion was assumed to be enough to activate the generator. Shortcoming. After designing the result, this design shortcoming were found. The buoyancy force was assumed to be the only force acting on the system. The BTO system has too many moving parts, which causing a large amount of losses. Design improvements. The improvement of each of these problems are as follows. A more efficient BTO system that uses less component is used. The factors that affect a body in contact with water are very complicated and depend on many variables. So the diameter of the buoy and the power figure were taken from paper written by Dr. Sahlawi that studied the condition of our location, and the value are 5 meter and 6 kilowatts.
Hello, my name is طيبة عبد المحسن الحبيتر. and I am here today to continue what Selma said previously.
Design assumptions. The assumptions made within the study are as following. The module has 1 degree of freedom. Nonlinear effect is neglected. Waves are plane or long crested. Water is an ideal fluid. The entire system moves in phase. Wave amplitude are small. Pressure taken to be uniform and constant. BTO system is assumed to be linear. The seabed is horizontal and fixed. Effect of the surface tension is neglected. Design description. Buoy. The result of this study shows that the optimal mass of the buoy is equal to 253 kg, where the spring stiffness equal to 10,006 Newton per meter, and the frequency equal to pi. For best performance, P-con 60 over 120 degree cylinder buoy is used. We have a single floating buoy that moves with the motion of the waves, is connected to an isolated arm that is bent to a platform. A direct drag BTO system was used where the isolated arm transfers the rotational motion to two generators, using a gear which connects directly to a moving rack fixed on the isolated arm. The gear is connected to a generator on each side. The gear's shaft is connected on each side to a free wheel using ratchet mechanism. Each free wheel is in operate when the gear rotates in one direction and is allowed to rotate freely when the gear rotate direction is reversed. This allows for continuous rotational and power extraction in both the wave rise and wave fall motion. The reason for using two generators instead of one is to minimize the losses due to momentum. A set-up gearbox is used to increase the rotational speed delivered to the generator. Knowing that the total vertical distance traveled by the buoy is equal to twice the wave height in one wave period, the average velocity of the buoy was obtained to be equal to 0.6 meter per second. Comparing our design with other devices with similar structure, the arm length was to be 5 meter. The arm angular velocity was calculated to be 0.12 radian per second. The applied torque is equal to 50 kN meter and the vertical force acting in the buoy is equal to 10 kN. This force was assumed to be the resulting of all the forces acting on the buoy. Velocity of the rack is equal to 0.24 meter per second. The rotational velocity of the gear is equal to 9 rpm and the torque applied to it is equal to 6 kN meter. Oscillated arm. An existing design with a working mechanism similar to the one proposed here was found and used as a guide to design the arm. The material chosen for the structure is aluminum alloy, since it is the lightweight anti-rust and has a yield strength of 240 MPa. A safety factor of 10 was used to make up for the unconsidered forces. The applied stresses on each member should not exceed 24 MPa. COMSOL were used to analyze this structure statically and dynamically. Multiple alternatives were needed to analyze the design. Initially, a 2D structure were used since it is easier to module. Stress analysis shows that the maximum stress in the structure is equal to 26 MPa, which is close to the criteria values. Then, a 3D module was constructed by connection two of the design section together using cross members, and the rack was added. Vibration analysis was performed again to check whether the structure is solid enough. The first and the second natural frequency for the final design of the arm are 60 and 29 Hz. These frequencies are larger than the wave's frequency, which make the structure safe and suitable for application. This is the technical drawing for the isolated arm. The rack attached to the arm will be custom made. The teeth of the rack are similar to the ones on the gear. The module for this rack is equal to 10 mm. The members are linked to each other using bolt joints. The maximum shear force applied to any member was calculated to be 15 kN. The largest span required has a diameter of 10 mm, and the material used is steel. Floating buoy. This is a technical drawing of the buoy. As mentioned before, it has a P-coin shape and diameter of 5 meter. Buoy to arm connection. The buoy is connected to an isolated arm using 2.5 kN force applied to each. The stresses was calculated and found to be 74 MPa in shear. A safety factor of 10 was used, as the force taken into consideration act only in the vertical direction. A roller bearing was suitable. Results showed that a 02 series cylinder roller bearing with a bore of 35 mm and outer diameter of 72 mm was appropriate. The diameter of the bend was taken to be 35 mm to match the bore diameter of the bearings.
Arm to platform connection. The forces acting on the connection point between the arm and the platform was calculated. These forces take into consideration the weight of the isolated arm, the 10 kN force acting on the buoy, and the reaction forces applied by the gear on the isolated arm. After doing our calculation, we get the same values as buoy to arm connection. For the pin exact, the value of the emitter was taken to be 23 mm, and the required material was aluminium.
Hi, my name is Shogil Khaldi and I will continue from where Taiba has left off.
Gear. The gear diameter was set to be 500 mm. A Spire Gear online calculator was used to calculate the suitable thickness for the gear, taking a safety factor of 2. It was found that the required gear thickness is approximately 50 mm. Two 13 mm thick keyways were made to enable the connection between the gear and the shaft. Output shaft. The output shaft is the shaft connected to the gear which transfers the gear's rotational motion to the freewheels. The shaft is made of steel and is 75 mm in diameter. The distance between the two bearings between which the gear is attached is 250 mm. Therefore, an 03 series cylindrical roller bearing with a bore size of 70 mm and outer diameter of 125 mm was selected. Freewheel with ratchet mechanism. The output shaft is connected to the external piece of the ratchet mechanism. One of these components is attached on each side of the output shaft. This component is then mated with the external piece of the ratchet mechanism. It contains spring-loaded flaps which allow the output shaft to lock when rotation is in one direction only. If the inner component of the assembly rotates in the counterclockwise direction, the spring-loaded flaps on the outer component attach on the grooves of the inner component, and the assembly locks and rotates together as one. At the end of a wave cycle, if the inner component stops rotating or rotates in the opposite direction, the flaps do not lock with the grooves, but keep skipping due to the geometry. This will allow the outer component to rotate freely relative to the inner component, acting as a freewheel until the inner component switches its direction of rotation again and drives the freewheel. Step-up gearbox and generator. As mentioned before, the torque applied to the output shaft is 6 kN/meter. A 7 kN/meter planetary gearbox was chosen. The gear ratio of this gearbox is 55:1. This figure shows the detailed dimension of this gearbox. Output rotational velocity of the gear and output shaft is 9 rpm. The rotational velocity delivered to the generator is equal to 509 rpm. The torque delivered is 117 Nm. No off-the-shelf generator was found. However, many generator manufacturers offered the possibility of manufacturing a generator with custom parameters. Manufacturing. The designed device is a large device that is intended to be placed in between Garo and Al Maradim Islands. This fact makes it clear that this is a large-scale project targeted towards the Kuwaiti government or large companies interested in the clean energy business. Due to the scale of the project, it is clear that the manufacturing and assembly processes must be done by professional companies with experience in off-the-shore equipment installation. Floating buoy. The floating buoy is composed of three sections, the flat cylindrical section and the two conical shaped sections with different heights. By combining these three sections, the buoy becomes very similar to an empty tank. Knowing that the three sections have a constant thickness, they can be made from flat thick aluminum plates that are rolled to the required diameter. Approximately 16-meter long flat plates are required to produce the required 5-meter diameter. After each plate is rolled into the required circular shape, the two ends are joined together using bolts or welding. It is expected that welding will be more suitable. The welding will be on the inside and outside surfaces to ensure strength and good sealing, which makes the entry of a welding operator inside the buoy necessary. This means that a manhole must also be created to enable the entry into the buoy. Due to the large size of the different sections, the use of heavy equipment such as cranes or forklifts will be required to place them in their appropriate positions. The buoy will be painted with a corrosion-resistant paint to prevent it from corroding. Oscillating arm. The oscillating arm is made from many rectangular shaped links that have different dimensions. The links will be made using extrusion. Holes will be drilled at the end of the links to allow for bolted joints. The gear rack connected to the arm can be manufactured in different ways. After research, it turned out that casting would be the most suitable method. The rack is a single solid piece that is made of steel and is connected to the frame of the oscillating arm using bolts. Output shaft. The output shaft is a simple shaft with keys attached to it. The shaft can be purchased ready with the required diameter. The keys are added to the shaft using welding. Finishing processes such as sanding are then performed to achieve a smooth finish.
Hello, I am Hanan. I will continue our project. Assembly. The assembly process for this device is rather complicated. The floating base of the device needs to be secured in the place using an effective mooring system that keeps it relatively stationary. After the floating base is secured, the bearings that connected the oscillating arm to the base is mounted. The oscillating arm is then mounted using pins. The buoy is then placed in the water and connected to the oscillating arm. After they are secured in their places, the gear is placed on top of the rack and the outboard shaft is inserted through the bearings and the gear. The freewheel, step-up gearbox and generator are then connected to the outboard shaft and bolted to the base to complete the assembly of the device. This assembly process of this device is rather complicated due to its nature and location. General step required to manufacture and assemble the device was presented. However, more details are required to complete the device. If the device is to be applied in real life, help from experts in this field will be used. Future work. The proposed device was designed such that all the components are placed on floating platform. To design such structure, some of the variables that have to be considered are the optimum shape of the platform, the material of the submerged part, the average density and total mass of the structure. Designing that is a project by itself and can be done in the future. Code and standard. In contrary to other energy sectors, wave energy generation is early stage of development and there are no established industry code and standard. Efforts are currently being made by IEC Task Committee TC 114 to develop industry code and standard for international approval, based on a review of existing code and standard developed for the offshore oil industry. Legal issue. Not all legal aspects were taken into consideration. However, some important points needed to be considered. In case the power plant is finalized, these points are as follows. Possible launch points must be labeled with warning stickers to avoid injuries. Safety procedure must be taken to warn the location operator about the high electrical current and voltage generated into electrical connection. The exact location of the power plant must take into consideration. The path of budget table shows that the total cost of all components within the energy extraction mechanism is expected to be around 11,130 kd. This is the cost required to manufacture a single unit that generates approximately 6 kW. The electric power necessary to cover the needs of island is expected to be approximately 120 kW per hour. This results in total energy generation of 1,051,200 kWh per year. This can be achieved by installing 20 of design units. For this rough economy study, which makes the total cost of the project 500,000 kd. In Kuwait, the price per kilowatt hour 30 fils. The cost of the energy generated by the designed power plant yearly is approximately 31,536 kilowatt per year, with a knowing that the initial cost of the plant is 500,000 kd. This means that the plant will take approximately 16 years to cover its initial cost. Conclusion. 9 different design concepts were generated. The design is chosen mainly based on simplicity and ease of implementation. Issues were found and improvements were made to finalize the design. The device was designed for maximum power generation. Details analysis is performed for individual components. The price of the device is expected to exceed 11,130 kD. Wave energy generation is economically challenging. Multiple units are required.